We present IntrinsicAvatar, a novel approach to creating relatable and animatable clothed avatars from only monocular videos. Given a monocular video, our approach can create a clothed avatar with decomposed intrinsic properties in less than 4 hours. The avatar can be then animated and relit under arbitrary pose and lighting conditions. There are 2 branches of approaches to the inverse rendering of humans. The first branch optimizes everything from scratch without data-driven priors on the material. This line of works models secondary shading effects, such as shadow and indirect illumination to a certain extent, by distilling visibility information into MLPs, or using simplifying assumptions such as spherical Gaussians to model lighting and material. Another branch relies on pre-training on ground truth 3D assets. Such approaches can often achieve high-quality results on within-distribution test data. However, it is very expensive to acquire such 3D assets on a large scale. Our method falls into the first branch, which optimizes a relatable and animatable avatar from monocular videos without any data-driven priors. We distinguish ourselves from existing approaches in that we model inverse rendering of humans as volumetric scattering with explicit ray tracing. We start describing our approach by formulating avatar modeling as an articulated NURF. Given any camera ray in observation space, we apply inverse linear blend skinning to warp the ray into a canonical space. In the canonical space, we use instant NGP to represent both the geometry and radiance of the avatar. Geometry is modeled as a signed distance field, and we use vol SDF to convert SDF values to NURF density values. This formulates a basic pipeline for articulated NURF. For physically based rendering, we sample points from the primary ray in addition to the radiance field samples. We query a material module to obtain the properties of these points, including albedo, metallic, and roughness. We then shoot secondary rays from these points to apply Monte Carlo integration to compute the radiance contribution from these secondary rays. We trace secondary rays by ray marching. Samples of secondary rays are fed into the geometry module and radiance module to query visibility and indirect illumination. Instead of following the standard rendering equation that was designed specifically for surface rendering, we trace back the root of the popular neural radiance field, which is the radiative transfer equation. We formulate the inverse rendering problem as a volumetric scattering process, which is shown to be more robust than surface rendering when abrupt depth changes are present. We refer readers to section 3.3 and section A of the paper for detailed derivations. We first show qualitative results on training poses and compare them to the baseline. As shown in the video, our approach produces much more realistic relighting results. We also show that our approach can generalize to novel poses under novel lighting conditions, while the baseline fails completely in this task. Here we show more qualitative results of learned intrinsic avatars under various unseen poses and novel illuminations, along with estimated intrinsic properties including albedo, metallic, roughness, depth, and normal. Finally, we show more intrinsic avatar results under novel poses and novel illuminations. Thank you for watching.